Um, our speaker is Matthias Peyer. Matthias is a brilliant professor in computer science to go along with all the rest of the brilliant faculty we have. So we will get him started in just a second, and appreciate your attention, and we'll continue on with Matthias.
I know I'm standing between you and lunch, but I hope I can still make it interesting and worthwhile for you to listen to me. This will be a more technical talk. As Cherry introduced me, I'm Matthias Peyer. I'm faculty here at Purdue in the CS department and affiliated with Sirius. In my group, we are protecting applications in the presence of vulnerabilities. So this is an interesting and slightly different approach from what we heard before. So in comparison, what antivirus systems or Tripwire do, they detect the modification of files, or they detect if there's some integrity violation. What we are focusing on is, on the other hand, we detect an active exploit before the attacker can actually do any harm. If you think about it, if the attacker is modifying files or modifying data on your system, the attacker already has a set of capabilities. You might need these additional checks, and they are complementing the work that we do. But we protect an active exploitation before the attacker gets any computational guarantees or can do any harm on your system. A lot of the work is done by the students in my group, and I would redirect all the praise to them. So there's 12 awesome students working on different forms of both compiler-based and binary-only based mechanisms, where we try to complement these. If you think about it, if you develop defense mechanisms, if you work on a compiler, you get more information, you get source code, you get all these other capabilities that you can work on. But there's always this one single binary or library that you are using that is a custom off-the-shelf library. So for an effective and efficient solution, we have to support both layers and actually support the binary-only solutions as well. So for this talk here, I wanted to use the time to tell you a little bit about control flow hijacking and different forms of attacks. And we've looked at defense mechanisms that we have deployed on our systems. And you likely know address-based layout randomization, or ASLR, data execution prevention, or DEP, and stack canaries, which are common defense mechanisms that have been deployed on our systems over the last 10 or 15 years. And we've made likely some progress, but can we quantify the process? How much harder is it now for an attacker to gain some form of code execution capabilities in our system? And if you look around and if you read the news, there's pretty much bugs everywhere in our systems. And we are being exploited again and again and again. And it's really hard to quantify, to know, or to see if we're actually making any progress at all. And we try to look into this and, on one hand, quantify the progress that we are making, and on the other hand, try to figure out what kind of next defense mechanisms we'll use in our systems on a broad scale. While in my research group, we are developing the next generation of defenses. We'll focus more on defenses here that are on the verge of being deployed. But I will still give you a peek into some of these future defenses as we go on. The pictures I'm showing here are from the recent Pwn2Own competition that showed that Microsoft Edge has been pwned 15 times, Microsoft Windows has been exploited a good 20 times, and so on. And there are bugs pretty much everywhere. So in the example here, we see that there's a calculator that has been popped on a MacBook Air, and the hackers received additional fame for controlling the LED keyboard as well and scrolling a message. You have been hacked by the group of people that did that. There's an Ubuntu system that has been exploited as well, popping up a calculator showing that an exploit has successfully triggered and the attacker got code execution. There's Microsoft Windows running. It's Windows 10 with an open shell where the attacker could compromise it. And also, a more interesting bug, you see here a VMware image or a VMware instance that runs a browser. And the attackers first compromised the browser. In a second step, compromised the Windows operating system. And in the third step, compromised the VMware instance to pop to gain control over all the running servers. So is it hopeless? Is everything we have deployed not effective? Or are we actually making progress? And let me go into detail for the questions that I just asked. There's trends in memory safety errors, especially all these exploits that are being used rely on some form of memory corruption at one point in time. Memory corruption is if you're thinking C or C++, some type safety violation or some memory safety violation. If you read out of bounds, if you have a function pointer that is not being used in the right way, or if you have any other corruption that is happening. And here, this is work by Victor van der Ven at Vrije University in Amsterdam. He plotted all the vulnerabilities and exploits that were reported over the last 16 years. And we can see trends, how they change and how they develop over time. So we see there's different groups: format string vulnerabilities, pointer vulnerabilities with some form of pointer modifications, integer vulnerabilities, heap vulnerabilities, and stack vulnerabilities. And we see that around 2006, 2008, there was a huge peak in stack-based vulnerabilities. And we saw a large amount of exploits. And conveniently, right around that time, we started deploying data execution prevention and stack canaries on a wide scale. And you see that all these stack-based attacks have been tailing off since then. So the attacks are actually effective, the defenses are effective against the attacks. And if you look at what kind of exploits are being used nowadays, it's mostly heap-based exploits used after free, different forms of used after free constellations where different memory objects are used again after they have been freed at a later point in time. So can we say that software is unsafe and insecure at any time? In the end, what we are using on our systems, we have pretty much everything implemented in C and C++. And C and C++ are programming languages that trade type safety and memory safety for, let's just say, some potential of performance that you can gain. You likely don't want to write your highly critical program in a high-level language like Java or something else, and to get the most performance out of it. Unfortunately, the systems that we have are too complex and too big to formally verify. And you've likely been at the panel yesterday about formal methods and formal verification. While I strongly believe that we should do as much formal verification as we can, there's just too much code out there to protect everything we have. That's why we need to have some form of defenses to protect the integrity and availability of our systems and data, even in the presence of vulnerabilities. Because if you think about it, for one piece of software, Google Chrome has 76 million lines of code. This is a humongous beast. This is all implemented in C++. And while Google has very strong coding standards and enforces code reviews, testing, fuzzing, and so on, there's still a large amount of vulnerabilities in these products. But it's not just Google Chrome that you are running with these 76 million lines of code. But in addition to that, you are using let's say the standard library, the libc, and the Linux kernel, which adds another bunch of code. So even if you're running your safe system, let's say you say, I'll program everything in a safe way, we'll do Python or Java. But still, the runtime system that you are using for Python and Java is implemented in C and C++. And it relies on the standard libraries on your system and on your operating system kernel, and on the hypervisor in addition to that. So you're building the trust of your system on all these other systems that are implemented with a low-level language. And as we know, the next vulnerability is just out ahead to bite us. And we're now in a time where vulnerabilities scale and can be used to compromise a large amount of systems. So you might ask yourself, how do attackers get onto our systems? And most of the exploits rely on some form of control flow hijack attack. So the attacker gains some form of code execution capabilities where the attacker tries to execute arbitrary code on top of your system. And many of you will likely know the code injection scenario where the attacker injects new code into the process. This is a simple scenario that uses a memory corruption to set up the initial attack, and the attacker overrides either some part of the heap or some part of the stack. and in the second step, redirects the control flow from the executing program to this newly injected data that is then interpreted as data. All attacks until around 2005 followed this principle. But we have introduced a large amount of defense mechanisms. We as a security community, not we as in my group, but these defenses protect against these attack vector. So this is no longer a thing. Attacks have become much more complicated. And attackers have resorted to a form of code reuse. So instead of injecting new code, because this is no longer possible given the defenses that we have, attackers have to reuse existing pieces of the code. Think of it as a jigsaw puzzle. You have all the existing code of your application, and you're grabbing little pieces of your application and then stitching them together in a new way that then executes the attacker's desired behavior. And a code reuse attack works with an additional step. And it's kind of similar to the code injection attack that I described earlier. An attacker first has to find the addresses of gadgets. Think again of the jigsaw analogy. You're trying to scan the code to find different forms of pieces of code that can be stitched together to then execute the attacker's desired behavior. In the second step, the attacker forces the memory corruption, similar to the first attack, and sets up the individual data. And then the third step redirects the control flow to a gadget chain. There's currently no active defense that we have that protects against this form of attack. On the other hand, there's a mechanism that is on the verge of being deployed, and it's called control flow integrity, that then protects against these forms of attacks. Quick question, who of you has already heard of control flow integrity? With a show of hand. Actually, a whole bunch of people. Do you use a product, a control flow integrity product, in your systems? Do you use Microsoft Visual Studio, Control Flow Guard? Anybody using that? Anybody using the LLVM CFI? One person, two persons that are both my students. That's interesting. Anybody else? Anybody using CFI in practice so far? Not yet, but this is the defense mechanism that is on the verge of being deployed. So you all will use CFI, I'm going to tell you, in the future. Right now, security products or compilers have CFI mechanisms that are available. You simply need to switch a compiler flag on and then use this defense mechanism in practice. So it's easy to deploy, even on existing code bases. You simply switch a flag, and then you are protected. For the others that didn't raise the hand, you might ask, what is control flow integrity? So control flow integrity tries to precisely limit the control flow of your application to the set of control flows that are well known and can be statically determined. So you restrict the program's dynamic control flow, so it can be executed at runtime, to whatever is intended by the programmer. So you're trying to get closer to the programmer intention with this mechanism. So it requires a static analysis that figures out all the valid targets for each indirect control flow transfer, limits the amount of targets that can be used at runtime to the set of static targets. And then a dynamic enforcement mechanism that executes this actual check. And we distinguish between two kind of edges, the forward edge and the backward edge. A forward edge is, for example, a function call. And these are indirect function calls, for example, a function pointer in C, or a virtual call in C++. So we're focusing on systems languages like C and C++ here, because they are, on one hand, the ones that are most used for all the software, and on the other hand, the ones that are most exploitable for these kind of vulnerabilities. And the backward edge is any function return, like the return instruction pointer on a stack. And we've looked at all the research that has been published over the last couple of years. So this was a highly active research area over the last 15 years. And it's slowly, the research is slowly winding down as we are progressing into active products that are used on a wider scale. And there have been 60+ research papers at top conferences that publish different aspects of CFI mechanisms. And it's an immensely complex topic. So we figured we'll look at all these mechanisms and try to figure out what their actual differences are. Are there opportunities for deployment that we can make it easier? Are there opportunities for optimization? Are there opportunities for higher precision to get more guarantees? And I'll try to tell you a little bit about these aspects that we looked at. But let me first start with what control flow integrity actually does. So for each indirect control flow transfer, we figure out the set of allowed targets. So if you have a call through a function pointer or a virtual call, we, through the static analysis, remember these are the only targets that are allowed to transfer control to. All the other targets will raise an error. Now, how do we do this? If you think about the C program or a C++ program, at one point in time, it will be compiled down into a machine code program. And the computer, the CPU, doesn't care where you're transferring control to. The CPU does not have any semantics on what targets are being allowed or not allowed. So if you have an indirect function call or a function return, if you're returning from a function, you can reach, or the CPU is happy to transfer control flow to any addressable byte in memory. Right? So this gives the attacker a large amount of different targets. So what does CFI do? It restricts those targets. Instead of just following this transfer, we verify the integrity of the function pointer before we use it to transfer control. So we add, during the compilation or during the binary rewriting, we add an additional check that says, check the current value of this function pointer to see if it is in the set of valid targets. If it is not in the set of valid targets, we will stop the execution of the program. And we'll do the same for the return instruction and limit it to a benign caller. So you are only allowed to return to benign caller of this function. So the attacker may still corrupt memory. But whenever we do a control flow transfer, we will verify the code pointers before they are actually used. And we protect against any illegal modifications of them. So CFI does provide some incremental security. The advantage is it can be implemented at very low overhead. But it gives us integrity of the control flow. If we look at the different CFI mechanisms, the strength of the CFI, the precision, depends on the power of the analysis. How small are these target sets? If you think about it, you can implement a CFI mechanism that is highly imprecise, that says, we will just allow any single function that is out there. And this is precisely what coarse-grained CFI mechanisms do. They say, we will allow you to transfer control to any function. This is still better than transferring control to any arbitrary executable byte in your memory. So instead of having a target set of every single executable byte, you have a target set of every function. This reduces the attack surface. Or you can have a fine-grained mechanism that further reduces the attack surface to a smaller set. And we'll get into detail for that. So we evaluated all these different CFI mechanisms using a qualitative analysis. And we distinguished them according to what kind of transfers they allow. And I have a simple example, and I hope it's readable in the back, that where we are using C++ here. We allocate a new object of type A, and we then do a virtual dispatch to function foo. And function foo takes two parameters, integer b and integer c. Now the question we ask ourselves, for a CFI mechanism, what kind of targets are reachable? Without CFI, any addressable byte is reachable. So any CFI mechanism will protect us against reaching an arbitrary byte. There are other CFI mechanisms that check for the arity. So this function here has a different number of arguments. So there's a class of CFI mechanisms that checks the argument. There's a class of CFI mechanisms that checks the return value. A void is different from an int, and we expect that it returns an int. There's CFI mechanisms that check this is a C function, while we are doing a C++ style dispatch. So we can remove this function. There are other mechanisms that say, hey, this is a C++ function, but B is not related to class A. Therefore, there's no valid way how we could dispatch over here. And there's other precision details that can further detect fine-grained class hierarchy differences. And hopefully, you will only have one single class that remains. So we looked through these 50, 60 different research papers and tried to distill it into some form of spider plots that give you some intuitive answer about the security guarantees of the different CFI mechanisms. And intuitively, the larger the size of the spider plot, the higher the security gains that you get. And this is some qualitative analysis that gives you an intuition of the different mechanisms. And in our paper, we have 1.5 pages of all these different mechanisms and compare them against each other. So we compare for the different control flows they support, the precision of the forward edge, the precision of the backward edge, the reported performance, and the quantitative security guarantees that they give. And what we learned is we as a security community, and this goes back to the panel from yesterday, we are doing a terrible job at actually quantifying and telling people what kind of static analysis we are using. Most of these papers focused heavily on performance. And in the end, all of these papers have similar comparable performance. And what we would like to know is what kind of security guarantees does it give you? Only if we know both the security guarantees and the performance overhead, we can assess if it is actually worthwhile to deploy these defenses. So we have to know both factors, performance overhead and security guarantees. Because maybe in a higher security environment or in a more sensitive environment, you're willing to pay more of the overhead cost compared to a low security environment. So you have to distinguish between those. And there's also a set of existing quantitative mechanisms like the average indirect target reduction, which did not really work out well because they pretty much counted how much they reduced the attack surface from reaching any arbitrary location. And it is the average sum over all the indirect control flow transfer locations divided by the number of bytes that are addressable. And if you think about it, this metric, if you only look at the libc, the standard library, and you allow any exported function to be reached, you already get an error value. This is the old metric of 99.9%. And we have shown that such a CFI mechanism can still be exploited. And there have been a set of black hat talks and other kind of talks that showed that this was not powerful enough. So what we did is we actually tried to compare mechanisms on a more realistic scale. So we compared actual mechanisms against each other on the same hardware, on the same machine, with the same benchmarks. So you can actually compare these different mechanisms, something that the research papers have not yet done yet. So we introduced new quantitative metrics, the number of the equivalence classes and the size of the largest class. Now, if you look at this, and this is likely a little bit overwhelming, so let me walk you through this figure. We measured the classes, the size of the classes, and the differences in the classes. What we are showing here are spider plots for the different mechanisms that we have evaluated on a logarithmic scale. And the red bar shows the average amount of allowed transfers on a per control flow transfer location. The bar shows the 25 and 75 percentile of the target sets. And the whiskers shows the individual outliers. So what we see here is a visual representation of how tight the static analysis is, allowing us to compare the static analysis against each other. In addition to that, we have a dynamic bar that shows what is actually used at runtime. So the closer we are to this dynamic bar, the higher the security gains. Also, what we see, there's several mechanisms that have a couple of locations where they are allowing more than 1,000 targets. So An attacker, if you put on your attacker hat, an attacker would try to figure out which locations are imprecise. Where is your dynamic analysis failing? And then pick these locations to attack the application. So this still gives the attacker some opportunity. But we see that sometimes even one single location dynamically uses a large amount of different targets. So there's a trade-off of how precise we can actually get for this mechanism. We also looked at the number of equivalence classes. So how many individual classes should you have? Remember, an equivalence class is, ideally you have one equivalence class for each indirect control flow transfer. Equivalence class meaning for each indirect control flow transfer that you have, for each virtual call, you remember this virtual call has this exact set of targets. All the mechanisms that we looked at merged these sets. So they have been reusing the sets, either for performance constraints or for other kind of optimizations. So they don't have individual sets and often have a lower number of equivalence classes, which leads to some ambiguity and additional attack surface for the attacker. So I talked a lot about the forward edge for indirect calls and virtual dispatch. But what about the return instructions? Return instructions push a valid return instruction target on the stack. And this can be overwritten through a simple buffer overflow. And what we figured out is that defenses without any form of stack integrity are inherently broken. So we need to protect the stack as well. And we have actually developed a defense mechanism that has now made it into LLVM as well, which is not yet actively being used. But again, this is only a compiler switch that you can activate to get stronger defenses in the future. Now, if you think about the attack, let's say you have 2 calls to bar to the same function. Now, as an attacker, in the second call to bar, you can override the return instruction pointer. And instead of returning to this location here, you're returning to this location. And the attacker has already implemented a loop. If there's some computation inside here that the attacker can modify, the attacker gains some computational capabilities. So we have to use some form of stack integrity, some mechanism that enforces stack integrity. So the attacker is restricted to arbitrary targets on the stack and cannot arbitrarily swap and loop through different targets, so that each target can only be called once and in sequence. So this concludes my part about CFI. CFI is the mechanism that you all will use in the future in the products you develop. And it's as simple as switching on a compiler flag. But I would also like to take at least 1 or 2 minutes to talk about another upcoming problem. Especially as we are moving towards larger and larger applications, type safety is becoming a very pressing concern. And we need to figure out a mechanism to protect our systems in the presence of type safety vulnerabilities, type violations. And most of you will be programming in C++ in industry, which is inherently prone to these kind of type safety vulnerabilities. And we are actively working on solutions for that are all, will all hopefully end up in some form of compiler at one point in time. So type confusion vulnerability, and this is exactly what is being used to compromise Chrome, Edge, Firefox, all these browsers out there on a day-to-day basis. Type confusion arises through illegal downcasts. So for example, converting a base class pointer to a derived class. And I have a short example here that illustrates this problem. We have 2 classes, class B and class D, whereas D is the derived class of B. So D specializes class B. Class B only has an integer foo, while class B has an additional integer and a virtual call, for example, BAS. And the problem that we are seeing is that initially a class of type B has been allocated, which only allocates this small memory area here. But then at a later point, a static cast to a D object happens. And the D pointer then ends up being here. And whatever is in memory and these other locations is being used instead. And this is what attackers use to compromise all our current software in these different mechanisms. So we are working on protecting against such vulnerabilities at obviously low overhead. Otherwise, these mechanisms will not be deployed in practice. So what we do is we replace, through a compiler-based analysis, each instance of a static cast, which is the source of the problem here, with a runtime check. So a static cast for a programmer, super simple, right? It just tells the compiler, hey, I want you to cast this object from this class into the object of that class. There's no check whatsoever, and you can cast from any object to any other object, and everything is fine. So we replace this compile time check with a runtime check. It forces us to track the type of each individual object. But we can, through this mechanism, enforce type safety for C++ and ensure that we are protected against these forms of vulnerabilities at low overhead. And we have one publication that I mentioned here, but there's other work ongoing where we further reduce the overhead and increase the precision. So let me conclude. Let's get back to the question that I asked initially. Are we making progress? And I started the talk by giving a set of examples of the Pwn2Own competition from this year. And I'm ending the talk with two pictures that compare Pwn2Own in 2007 and Pwn2Own in 2017. 10 years later, have we made progress? 10 years ago, it was a one-man show. One single person compromised the system. Nowadays, we have teams of 20 to 25 people that compromise these systems. So yes, we are making progress. Exploitation has gotten much harder and requires a large team of highly skilled people that actually figure out all these dependencies and generate these complete exploits. So yes, we are making progress. Attacks are much harder and require large teams, not just single player. And CFI, the mechanism that I talked to you, makes attacks even harder and much harder nowadays. Some attack surface remains. So this is not the end, but it is something that further adds an order of magnitude of difficulty for the attacker. And we can use stack integrity, data execution prevention, ASLR, and so on as complementary mechanisms. Ongoing work as a community, we have to work on precision for CFI to increase the effectiveness. We have to work on type safety, and ideally, at one point in time, in memory safety. And with that, I would like to end my talk and ask if there are any questions. Thank you.
How applicable is CFI to interpreted languages like PHP?
This is a wonderful question. Thank you. And I tried to tone it down. So CFI gives you additional protection. It makes attacks harder. And your question is excellent. How effective is it in the presence of an interpreter? Like an interpreter allows the attackers through data-only attacks to stitch together a new program that is then being interpreted. Now, with the difference, without CFI, the attacker would simply inject code and execute arbitrary system calls and arbitrary commands. With CFI, the attacker is restricted to modifying the actual code that is then interpreted by the interpreter. Let's make the Java example that supports Java security modules. So you're restricted to the Java security modules that you have, restricting the code that you can actually execute. So it still gives you some additional guarantees. The attacker is then restricted to the interpreted language and not to the machine code language. Also, the attack gets much harder because the attacker has to work on the machine code, on the interpreted language basis to then try to escalate privileges accordingly. And as I said, CFI is not a panacea. You likely use additional system call filtering, system call policies, other integrity mechanisms as well. Did that answer your question? More or less? Okay, thanks.
Hi. I'm wondering, how does the Intel control flow enhancement technology fit into kind of the big picture of what you're talking about?
Wonderful question. Thank you. Yeah, for Intel CET, for those that don't know it, is a hardware implementation of CFI. Let me split this question into two components, the forward edge and the backward edge. Interestingly, for the backward edge, Intel CAT implements a precise shadow stack. This is wonderful. This is exactly what we need to get stack integrity. So I guess in the future, we will all use Intel CAT on Intel machines for the backward edge, because it gives us strong stack integrity at negligible overhead. This is perfect. For the forward edge, the precision is rather loose. So Intel CAT allows you to tag functions that are valid targets with a specific, let's say some form of tag, right? And then any indirect control flow transfer is allowed to reach any of these tagged functions, which is highly imprecise. This is, again, this single target set mechanism, which is pretty much the same as Microsoft uses in their control flow guard. So this is likely too weak in practice to be effective. So it makes the attack somewhat harder, but doesn't stop an attacker. And it's near close to where CFI can go on a precision basis. So people will likely use it. An advantage of Intel CAT is that it's very fast. So people may use it for the forward edge in low security context, and in the backward edge for pretty much every single context. For the forward edge, people will likely switch to more precise solutions that give you stronger guarantees, which are hard to accomplish on a hardware level. So Intel did as much as they could without significantly complicating the underlying hardware design. Good question. Thank you.
All right. Thank you.